Hey, thanks for tuning in. I'm going to try my best to help you get through this analysis that we've been working on the ionic compound data set. So the name of the game is we're trying to explain in writing some of the relationships between the structural features at the atomic level of these ionic compounds and their laboratory scale properties, things like melting point and solubility and stuff like that. Okay, so just to remind ourselves, we've been looking at some features of the crystal lattice structure of ionic compounds, and this is the list of compounds that we've been working with. There's 20 of them. And you can see it's a very nice uniform data set. They're kind of a closely knit set of compounds, and what they share in common is each compound is composed of just two atoms, right? So there's one, let's take sodium chloride, that's familiar. One atom of a metal and one nonmetal, all right? And furthermore, the other characteristic that they share is that the metals all have a single positive charge in the ionic state. Whereas the nonmetals, fluorine, chlorine, bromine, iodine, they all have a single minus charge. So the charges are single plus, single minus, and so it makes a nice kind of homogeneous set of compounds to do some analysis with. So when we look over at the structure of the lattice crystal, you can see that there's this beautiful alternating pattern between the cations and the anions, and that makes good physical sense, because if you're a positive, let's say, sodium cation, you really don't want to be fraternizing with other positively charged sodium ions, right? You want to be surrounded by negatively charged ions, because that's what you're attracted to. Okay, now the other thing to remember is, as we progress down this table, as I have it organized here, the distance between neighboring ions in the crystal lattice is going to increase, right? Because the atomic radius of these ions is increasing as we go down. So what happens is that leads to ionic crystals that are bigger and bigger with larger and larger internuclear distances. Okay, so internuclear distance is a term that we've talked a lot about. Okay, so here's the full data set. Here's all the compounds here in the first column, and then I have lots of a lot of properties, not only the internuclear distances, but melting points, lattice energies, and solubilities in water. Okay, so you're all too familiar with this data set. You've been working hard on this in the computer lab. Here is one of the correlation plots that we've been looking at, where we're trying to relate internuclear distance with lattice energy to see if there's any relationship between these things. And when we examine this association between these two properties for this data set, we find that there's a correlation of with an R squared of 0.86, so it's pretty strongly related. Very interesting. So let me back up for a second. So you guys have, I'm very proud. You guys are getting really good at taking a kind of a large sprawling data set and generating any kind of scatter plot that you want to look at, and then you know how to label it. You know how to format the graph with axis labels and a reasonable title, and you know how to adjust the minima and the maxima of the axes so that the data points use up all the white space. So, and you're familiar with line of best fit and R squared, and so that's great. That's a set of skills that I think you're going to find very useful going forward. Now, beyond the technical skills, however, now we want to go a little deeper, and we want to step back and think in some depth about what some of these correlations really mean, and see if we can connect them to scientific principles. So to that end, we are right in the middle of this analysis task, right? Where look at down at the bottom here. These are the three pairs of properties that we're trying to write about and explain. And so in this presentation, I'm going to focus on internuclear distance versus lattice energy. And as you know, these are the three things, the three questions that we're going to be addressing in our written analysis. Do you see a correlation? Characterize what kind of a correlation is it? How strong is it? But maybe the most challenging part is number two here. You need to look at correlations and think about whether there really is a direct cause and effect link, and if so, describe what's the physical principle behind it. So to kind of help you get started, what I did was I took a stab at writing my own analysis for this first one, distance versus lattice energy. And I just want to say at the outset that this is by no means the gold standard. You don't want to copy what I do, because hey, you may come up with something even better. And there are many ways, many different paths to writing an excellent analysis, and you're going to find your own. But I thought, just to give you some, a little more structure and support in your effort to write this analysis, I'll just show you what I wrote. So quickly, here is the analysis that I came up with for distance versus lattice energy. So maybe push the pause button and just kind of read through it quickly, and then we're going to dissect this. Okay, so I hope you've read through the whole thing, and now let's dig in. All right, so starting from the beginning, and I'm putting these two plots up here just sort of for reference, so we know what we're talking about. All right, so the first paragraph, I just want to give the facts. Okay, so at this point in my written analysis, I feel like the reader doesn't really care about my personal opinion or my interpretation of the data. I just want to give the reader the facts, in a very concise format. So the first thing I say is that the data show that there is indeed a correlation between internuclear distance and lattice energy. All right, so I'm naming the two properties that we're talking about, and I'm using some clear descriptive words to describe the nature of the correlation. So I'm saying that it is strongly correlated. I'm kind of going out on a limb there, because I know the correlation is 0.86 here for the first data set, and I'm going to help the reader by further describing it as an inverse correlation. So in the very first sentence, the reader's going to know exactly what kind of correlation I'm talking about, how strong it is, and whether it's a direct correlation or inverse. But then the second sentence is where I get quantitative about it. So I'm going to tell them the data, the results of the analysis, and here are the two correlation coefficients. So the reader knows exactly what the story is here for those first two data sets. Okay, now, next, we need to commit to whether we think there's a cause and effect relationship here. And so I just come right out and say it. I do believe that this association is firmly based. So I'm being a little strong there, right? I don't think it's just kind of based. I think there's no doubt about it that there is a cause and effect relationship. Now, that's my claim, and here's the linchpin. Here's the center of my argument. I am basing my claim on the fact that I think this correlation is based on Coulomb's law. I think that that's the physical principle that explains the correlation that we're seeing, and that's really important. Coulomb's law is one of the most important physical phenomena in physical science, and here we go. So the reader at this point may be thinking, Huh? Well, what's Coulomb's law? What are you talking about, man? So I'm going to spell it out. I'm going to be try to be as clear as I can in defining what Coulomb's law is. So here is the equation form, and you guys that are going to go on to physics, you're gonna learn about this in a little more detail. But it is a hugely important principle in physical science, and so I'm really delighted to introduce it to you if you haven't seen it before. This sentence right here that starts, Coulomb's law provides a mathematical. So what I'm doing here is, in words, I'm basically unpacking the mathematical formula. All right, I realize, not you need to realize not all readers are, absolutely fluent and comfortable with mathematics. So you need to paraphrase it for the reader, and make sure that they are with you. They're coming along with you on this journey through your analysis. Okay, so between text and the actual math formula, hopefully you've covered most of your audience, and now they kind of get what you mean by Coulomb's law. All right, so yeah, hopefully that's what the reader's saying. Now, but then they're going to turn around, they're going to say, well, that's great, but how does this relate to anything? What's this got to do with ionic compounds? Okay, so this is where you start to this is where you're going to make that connection for them. You've got to build the bridge between this somewhat abstract mathematical formula and the physics of what's going on in your in this ionic compound. So you say, for each cation anion pair, this can be thought of as a pair of charged particles that can be represented as Q1 and Q2, and the internuclear distance between them can be represented as D. Okay, so if we back up just a second, so Q1 and QD represent the magnitude of the charges on the two ions. And in our data set, remember at the beginning of the video, I said that the charge for the metals was a single plus, and the charge for the nonmetals was a single minus. So Q1 and Q2 are both equal to 1, but they're opposite in charge. And then D stands for distance. Well, in this context, the D is going to stand for the internuclear distance between the two ions. All right, so that's what this paragraph is about. And then here's where the next paragraph is, hopefully where this is where we set the trap. This is where we're going to try to create the airtight argument that connects Coulomb's law with what's going on in an ionic compound. So if we read here, for a closely related set of ionic compounds, as the distance between oppositely charged ions increases. Okay, so here I'm using the language of Coulomb's law, right? D stands for distance, but then in parentheses, I'm going to try to reinforce that connection between Coulomb's law and an actual physical thing like the internuclear distance between ions in a crystal. The energy of attraction between ions will diminish, leading to an overall decrease in lattice energy. Okay, so again, here in the sentence I'm talking about how as the distance between the ions increases, as we go to bigger and bigger atoms that are spaced further apart, Coulomb's law says that the energy of attraction between the ions is going to go down, right? Because the D in the equation was in the denominator, and as we make that denominator bigger, the whole expression, the whole fraction is going to get smaller, and that is what leads to a decrease in crystal lattice energy. Okay, so here I think we've constructed a good argument, and now we're ready to close the deal, and that's where the last sentence comes in. So here we kind of come back full circle, and we point to the correlation plots that we saw at the beginning, and it's almost self-evident now. We look at these and we say, oh yeah, as we go to different compounds that have larger and larger internuclear distances, it's really clear that the lattice energies are going down. And now, hopefully, we know why, and hopefully our readers understand why. That's because when you move two charged particles further and further apart, the energy of attraction is going to go down, and that's going to lead to the lattice energy going down. Okay, so now here's back all in one piece, in text form. Here's what the analysis looks like, and what I want to point out here is simply that it's not that long actually. So if you look at this entire thing, the two plots, these are taking up a lot of space, right? So if you exclude the two graphs, then you've got, it's like not as long, and then you've got the equation which takes up some real estate here. So if you exclude the equation and the two graphs, the amount of text that's required to give your observations, set the groundwork to your argument, and provide a nice description of how Coulomb's law relates to ionic compounds. It's not that much. It's not that many words, right? So you can definitely do this. No doubt about it. Okay, so now with that as an example, I'd like you to take a shot at these other two pairs of properties. Neither melting point nor solubility are as complicated really as lattice energy. So let's give these a try, and then we'll see how we do. All right, thanks very much.